Oliver. Let's take it from here, and we'll turn it over to you. Thank you so much, Dr. Branch, and your partner, Dr. Wolfenheimer, is not able to attend today, but I'm sure you can give us a little background on your team. Just kind of introduce us to your group and your studies with the Earth System Solutions.
Certainly, yeah. I'm just going to share my screen. How do I do that? Oh, yeah, here. It's not doing anything at the moment. Okay. So can everybody see my slide here?
We can, yeah, and I'm sure you're going to touch on it because your first image just says these are applications around the world. So I love that that's part of this conversation. But yeah, we got you on screen.
Yeah, great. So thanks very much for this nice invitation to be here and just to be part of this fantastic project. I think these regional climate engineering and climate adaptation projects, which are really multidisciplinary, this is definitely the coming thing. I think we're going to see a lot more of these, and definitely using models of different kinds of applications is definitely going to become the norm, I think, to do environmental impact assessments and also how to design these projects as well. When you have knowledge of how the Earth system is working, then we have the possibility to also place these projects in different places where they will make the most impact or where they will do the least damage. So I think this is fantastic project. So yeah, I met David Mitchell at the AGU last year, was it? And yeah, he saw my presentation and said, okay, you might be interested in this group, and introduced me to Nathan and Rob and this project. So of course I jumped in. So I'm from the Institute of Physics and Meteorology. So I'm a scientific researcher, and I'm basically a modeling hooligan. I work with WRF mostly, but I do measurements as well. And we also have a commercial arm, which is Earth System Solutions, depending on the application. So I'm coming basically just from a slightly different angle. Go on to the next. Yeah, so I'm going to talk about a couple of case studies using downscaling models. So both of which involve arid or semi-arid regions and changing the land surface and trying to guess or trying to assess what are the impacts on the climate. So the first one's about revegetation of desert regions, primarily with plantations of xerophytes, for instance, jojoba. And the second one is seawater flooding of a depression near the Caspian Sea. So you can see where there's some overlap with this project. And yeah, then I'm going to talk a little bit about some modeling strategy at the end. So I'm working with these overarching questions, at least in my mind. So how does the atmosphere interact with land surface changes, for instance, such as those as would be caused by Laguna Salada and Salton Sea restoration? How can we investigate potential impacts with models? And therefore, what are the implications for the Laguna Salada projects under a changing climate? So just for those who are not kind of in the modeling world or not so deep into it, I'll just explain downscaling. Most of you have come across downscaling models before because these are basically what's used in weather forecasting models, except generally instead of looking into the future, very often in research we do hindcasting. So we just run the same a global model. We take the data from a global model, which are running all the time, and we just use these boundary conditions around the domain. Depending on your application, you can choose the size and the resolution. And then you just take those boundary conditions and drive a higher resolution domain usually with a different model. And sometimes they're driven every 6 hours, but this can also vary. So, and very often embedded within these are smaller domains, like nested domains, usually becoming higher resolution. Now, higher resolution models, they can give a higher resolution of processes going on in the atmosphere, but a lot of people don't think about also the resolution of the land surface, which is extremely important. So here you have a 1.25 degree resolution land surface represented in a global climate model. And as you can see, it's very pixely. So the whole of the Czech Republic here is represented only by a few pixels. As we go down in resolution here, down to about 40 kilometers resolution, yeah, we start to see a little bit more. And then down to 10 or 11 kilometers, and it starts to be resolved. And then when we go down to so-called convection permitting resolution, we really start to get a nicely resolved landscape. So particularly effects of mountains, but also land use, different patches of how wet the soils are. This is all very important to get a good simulation. So this really does make a difference. But of course, the higher resolution you go, the more expensive it is, and usually the shorter the simulation has to be. So just a little introduction to downscaling. So our group, and particularly my research, had focused ever since my PhD on desert land use change and deliberate land use change in the desert, and how this interacts with the atmosphere, and even how this could be controlled to produce rainfall or convective rainfall. So we were actually involved in a project also in the UAE, or the Arab Emirates, on a very large rain enhancement program, which was mostly dominated by cloud seeding research. But we were bringing a new angle, so we were also introducing ideas about how to modify the weather using processes at the land surface. For instance, the introduction of very large plantations to create actually heating in the desert. And we had some very nice simulations there, which I'll discuss in a bit. So this whole concept came from a carbon farming concept, which was done also from our institute. Professor Wolfmeyer and Professor Becker, they came up with this multidisciplinary concept paper here, based on a Jatropha curcas plantation. So this is grows nicely in semi-arid regions. And this is based around a concept of a very large plantation with its own bioenergy power plant and desalination. So this is generally designed to be a coastal plantation. So various potentials, which I won't go into too deeply here. So carbon sequestration, commercial revenues, land reclamation, and the fact that these are becoming slowly more feasible, these very large plantations, with irrigation technology and sciences, use of urban wastewater, especially if we're using non-food crops, and also the maintenance of food security, because we're only utilizing marginal land. So we're not interfering with land which can be used for arable other crops like wheat or corn. So my primary area of research was to see what these effects had on the climate. So these changes in land surface fluxes and exchanges with the atmosphere. So several papers later can show you some of the results. So this is a simulation of a large jojoba plantation in Oman on the coast here. So done in the WRF model at a resolution of 2 kilometers. And also in the model, it was a simulation. I added a simulation of subsurface irrigation. And what happens here is you can see basically this orange color is a heating of the atmosphere. Now, typically we associate plantations or irrigation with a cooling effect. But actually with these very water use efficient xerophyte plants like jojoba, they can close their stomata very much during the day. And actually during the day, you get a strong heating effect. And here we have the process chain by which these plantations can lead to convection. So very simply, you get a higher absorption of solar radiation because it's a darker surface. You get also this stomatal closure, and this leads to an increase in surface temperature over the canopy, not necessarily under the canopy though. This creates a heat low, and an increase in surface friction also increases turbulence. And then under the right large-scale conditions, this leads to convection initiation and then can lead to rainfall. Now, this heating sometimes surprises people, but I have actually measured this. So you can see this little graph here, and these are 2 meter temperatures over jojoba, Jatropha, and also over the surrounding desert. and it can easily be 3 or 4 degrees warmer over the plantation than it is in the surrounding desert. That's a huge difference, mainly because the desert is reflecting most of the radiation, so there's much less available to turn into heat. So even though you do get some evaporation, so 150 watts of latent heat, you still get an increase in heat over the plantation. And it's this mechanism that we're using to create a heat gradient spatially, which can lead to a circulation or a rising air mass and then to precipitation. So we developed this further, and we looked at the background conditions where this was necessary to trigger this convection. And based on this work by Kirsten Findell, who's very well known, she came up with these indices here. And we were able to, basically based on instability, so temperature profiles above, the moisture content in the middle atmosphere, and also wind dynamics, we were able to develop an index whereby we could see where in the world are land-based interactions most likely to happen based on heating or differential heating. And here you can see in these hot regions, so the Sahara Desert and the Arabian Peninsula stick out here. So where you have the higher index values, you're more likely to get this triggering effect from the plantations. What's also very interesting here for this region is that during the summer or the time of the monsoon, you also start to get very high values in this region as well. So even in areas where you do have a strong inversion, the atmosphere is basically primed for some kind of convection if the inversion can be broken down, and usually if there's some kind of added lifting effect, whether it comes from heating or a frontal system or a mixing of or even mountain flows. So I looked into this also for specific locations in the region. So here you have some areas in Baja California, and here we can basically see the lapse rate, or which is the stability. The instability in the troposphere. So it's a little bit higher up than the boundary layer. And then along the bottom axis, we have the surface humidity. So, and then we have the months of the year. So you have basically a climatology. This is based on ERA 5 data for over 30 years. And then also here we've got temperatures, and we've also, I'm clicking it forward. And we've also got precipitation. Now these are based on NOAA data, and I guess these are based on gauge data. So I don't trust these fully, but I think it gives a general idea of what kind of conditions exist. So definitely in North Baja, Ensenada, I guess this is on the Pacific coast. So you have basically primed conditions, very high instability higher up in the atmosphere. But at the same time, during these months, you also have the lowest rainfall. And very likely this is due to be inversion or a stable layer very close to the surface. However, this means that if you were to have a strong mechanism at the surface, some kind of surface heating, you could well break through this and lead to deep convection, but otherwise it's suppressed, even though you have high unstable conditions. But I'll leave this to the guys who really have experience with the local region to tell me you're incorrect, or sometimes we modelers, we think we know a place because we've looked at lots of data, but there's nothing quite like going there. So this was quite nice, these findings, because we also had some preceding simulations we did, which was right in the same region. So here, just a little bit to the east of the Laguna Salada region. So here we put a giant plantation here just at the top of the Gulf of California. And this was before we did the other work. And here also in the summer, we got a very strong increase in precipitation over the plantations. Now these are huge plantations, like I think it's 100 kilometers long, but we just wanted to get a large impact in the simulation to see how it would work. So there you can see the increase in precipitation. So although we've looked at dry plantations, of course, there are other kinds of dry land vegetation that could be used. So these halophytes as well that we've been hearing about. Jatropha is another possibility. And I see that these kind of ideas could possibly be combined with Laguna Salada salton sea restoration, perhaps to using the water for partially desalinated water to irrigate these kind of crops Okay, mangroves I don't know much about, but certainly for these xerophyte crops, which could be used, and perhaps this could be thought of in the future. Okay, so now we come to the second case study. So I'll try to go quickly through this. I guess we're short of time. So we were asked to do a simulation of a flooded depression close to the Caspian Sea. Actually, this is in Kazakhstan on the coast. There's several countries around here. Basically, to look at the regeneration of this dry land. This is a very harsh environment here. It's extremely dry, very hot in summer, very cold in winter. And the idea was to provide a new coastline and a port. So there's a lot of industry around here, especially the salt industry. But they wanted to find out what the environmental impacts were and climate interactions. So they asked us to actually do this. So just zooming in a little bit closer there. So the Caspian Sea itself is 27 meters below sea level anyway. But there's a depression here, which is up to about 120 meters deep, quite close by. And the idea was just to flood this area with water to create, some kind of new, a new port or protected port. And you can see here, just for scale, this is 90 kilometers long here. So it's extremely harsh environment. So it gets quite hot during summertime, but almost no precipitation at this climate station here. So it's very, very dry. So using GIS, so I just did basically all the water below, all the area of this depression, which was below the level of the sea level, we just filled it with water inside the GIS. So just created a new mask, basically. Turns out the area is about 2,500 square kilometers. This is about 3 times the size of the Salton Sea, at least the figures that I just looked up. So just to give you an idea of the scale. And then this is just put into the model and used as the land surface data. So just to give you an idea of the lake depth, so varies between 100 meters. So there's kind of a bit of a mountain there, which comes up close to the surface. But this is the shape of the depth. And here you can see some profiles across the depth, across the lake. So just here's the details about the simulation. So we have a very large simulation covering the whole Caspian Sea, and we did a comparison between a control simulation, so with no flooding, and another one with flooding, and we ran this for 1 month at a resolution of 2.7 kilometers during summertime, and we looked at hourly output from the model. Also added onto the model at this point was kind of an improved lake model, which gives you more vertical layers, and this gives you good transfer of heat mixing, and it also includes 10 soil layers underneath and 10 bedrock layers under that. And the idea is to really provide very reliable fluxes to the atmosphere, as this would happen in a real water body. So this could be something to think about for modeling also the depressions. So just give you some nice results now. So here we have a comparison of 2-meter air temperatures. So this is the average over the whole month. And if you just take a difference plot, we can see there's a net cooling effect. So up to 5 degrees cooler on average in some parts of the lake. Here you can see different areas of the lake are different temperatures, and that's the lake model really working. So it's really showing that the shallower parts of the lake are really heating up much faster and cooling down faster than the deeper levels as well. So we've got a net cooling effect. Maximum temperatures are much cooler, so up to 9 degrees cooler centigrade. So you can imagine the kind of effects you would get. And at nighttime, the minimum temperatures, as you would expect, these are warmer as the land cools very quickly around it. So it's basically a buffer for temperature extremes. Yeah, here the advantage of having hourly output is that you can look at diurnal cycles and see what's happening throughout the day. So we don't have to look at everything here, but notably the evaporation here is expressed as latent heat, which you can just swap into millimeters or acre feet. So during the middle of the day, we're getting a huge evaporation, as you might expect. Although the humidity drops down in the middle of the night, as the boundary layer increases in height, this moisture is mixed much further up into over a thicker layer, so it seems to go down. But again, 2 grams per kilo difference over the lake as you have over the dry depression. But this is more than enough to make the difference between a thunderstorm triggering or not. So over the month, total precipitation, so this is just the accumulated value. So you can see here differences. Now, I hope you can see the coastline here, and also the outline of the lake. So basically over the ocean or over the Caspian Sea, you can see a large increase in precipitation there. And also at the back of the depression, we can also see a large increase, especially around the bottom there, up to 30-40 millimeters. We also, have this increase at the lee side of the precipitation of the depression. The wind direction is going generally west to east. So this could be caused by there's like a ridge at the back of the plantation. It's not a plantation of the depression. It's not particularly high. It's about 50 meters higher than the water surface, but that could be what's causing this lifting effect. If we look at the mean wind field, we can see that there are some small changes, especially out to sea. So there's some impact on the wind field, the wind circulation, even quite far away from the depression, and also, of course, over the top. But of course, with averaging, we lose a lot of information. So here we look at hang on, I'll just skip forward here. We look at a snapshot. Actually, nearly all the rainfall that fell in this 1 month actually fell just on one day. And if we have a look at 2 hours before this precipitation occurred and we compare the wind field again, here at about 150 meters high, we can see there's a definite big difference in the wind field. So caused by this is the flooding here. And we can see just going over the coast, we can see this a big difference between the two simulations. So here we have a very strong convergence line at the close to the surface, and this more or less corresponds with this this large area of precipitation here. So you can see that it's really having an effect, and this is really happening before precipitation is occurring. So you can see this is the pre-convective environment is modified, and it's really having an effect on rainfall. If we take the overview, we can see just in our region here that there is an increase in rainfall. So even though this depression here is very close to a very large water body, it even shows that there is an impact here, okay, although it's a larger area. But I think you can see that there's definitely an impact on the precipitation, at least in the model. So I think that's quite encouraging that it can make a difference. We do notice also in some other areas of the simulation that there are also some tiny differences. And this is actually one feature when you do comparisons in a model, is that the differences in the land surface conditions, they can propagate as rounding errors, and they can go right through the domain very far away from the change itself, which aren't physically consistent, but this is basically just to model rounding. But these should be quite small in comparison with the main impacts, especially close to the change itself. But I think that's quite a nice result. So I'm going to wrap up there and just summarize. As flooded depressions, we have a reduction in temperature extremes, an increase in humidity evaporation, as you might expect. Local wind circulations are altered, and sometimes over quite large distances. And we have an increase in precipitation, 11% within 100 kilometers distance from this particular addition of flooding. Plantations, I call them dry plantations because these are very minimal irrigation. These can increase rainfall through surface heating gradients, and this is very much dependent on cultivation type. So very wet irrigation, or where you use sprinkler or furrow irrigation, this might not happen because you're more likely to get a cooling effect. But in theory, it might also be possible to reverse this effect. So if you have one area which is very hot surface and another area is cool, you might get the same impact, even though it happens the opposite way around. So the other nice finding here is that the North Gulf of California region is definitely a hot zone for impacts. So changing the land surface could definitely well have strong effects. And there is a potential for combining these flooding and vegetation strategies to perhaps increase this effect. So modeling is an excellent tool for an investigation of these kind of environmental engineering scenarios. However, a well-defined modeling strategy is probably going to be critical to make sure we get the best result and we really get the answers that we want, and that we use the right kind of model simulation. So I'm sure there's going to be a lot of talk on that.
Yeah, and the right parameters, but also the right timing, right? Because we talked about that in the meeting originally, is you have to predetermine the time. So we would want to say it maybe is specific to those summer months in July, August in this particular region, and then a datum that's over the course of the whole year to show, the overall validity.
Yeah. I just got one more slide that I did here because I was thinking, I wanted to say that framing the research question is so important for this, because depending on exactly what question you want to ask or answer, and could completely change your modeling strategy, or at least as I see it. So you may do one where you have to run a simulation for a period of years. But then, because it gets more expensive, you wouldn't be able to use as many scenarios. But if you just want to look at local impacts and to see, okay, are we getting an effect? Maybe then you could do lots of different land surface scenarios, but you just run it for a shorter period of time, such as the one season, or maybe one season in a cold year, one season in a hot year. You could do something like that also. But it really depends what you want to find out. And I think that's worth making that discussion in quite detail, because, for instance, if you want to look at attribution of rainfall, one question is, could upstream Colorado Basin rainfall be attributed to water evaporated from Laguna Salton Sea? Now, this has been done before but this may require something like a tracing model, which can be bolted onto WRF. I personally don't have experience with this, but I know people are doing it. You can use this to look at teleconnections. You can even look at transport from one river basin to another. But yeah, that's quite difficult to do, I guess, and something would be quite an investment in time as well. But yeah, so I just wanted to basically make that point, that I think it's definitely, your strategy will depend on really what the focus is.
Yeah, and just on that note too, it's really interesting. There's people that are studying this for the Caspian Sea because it's a depression, right? That the cost and the viability of flooding it is not very severe. So if there's a net positive benefit, the cost benefit analysis proves itself out. The value of that water that drops 100 kilometers away due to the cost of making that depression a resource becomes negligible, and it's an investment rather than an impediment.
Absolutely, yeah.
I do find it fascinating, Dr. Branch, that the concept of essentially increasing the local albedo via growing such things as these salt or selenium gathering plants that we can irrigate with some salt water may provide a effect that would be beneficial. And I think that's something that needs a little more cooperation with some of our other partners.
Yeah, that's a good suggestion. Yeah. I mean, my dream is to produce a controllable way of doing this. So, for instance, if you had a very large jojoba plantation, and if you forecasted the conditions, let's say for the next week, the atmospheric conditions are perfect, and then you switch off the irrigation, the plant can easily handle that in most conditions, but it will close the stomata, and you'll get a real fast heat bloom, which will last for a couple of days. This is one way that you could really increase this effect. So this is and
it's even more interesting when you say we need more, and then run the model and plot it in one spot to say, is this going to affect it? And then that should be the place of your regenerative resources, seawater agriculture. You can plot those zones to know if it's the highest best use. If it's not, you replot it in a different section. If you notice that it's working and you need to expand that, you can expand that. So it's really the fascinating thing is it's kind of gamification of geoengineering and cloud seeding, but it's actually doing it with an economic benefit, and so those are the financial mechanisms that we keep coming back to. There has to be a financial mechanism to get these things done, and you've just proved it. If it's being studied at the Caspian Sea, it has those mechanisms built into it.
Definitely, yeah. I guess most of these projects, they know one of these benefits would be enough to justify it. It's a slice of the pie, right? So you have some large-scale desert vegetation, which you can sequester a lot of carbon, but that alone is probably not enough to justify the cost of irrigating such a thing. But if you can load these potentials together, as you're doing, then it definitely starts to become, but it's just more difficult to analyze, I guess, because you need more. It's really multidisciplinary, right?
Absolutely. Well, thank you so much,
Oliver.
Dr. Branch, thank you so much for stepping in. Dr. Mitchell, both of you are very complementary to each other, and hopefully, in the very early stages, we're going to be working on these and getting them started. That's our primary goal right now, in and amongst everything else. So I appreciate you stepping in and sharing this with our audience, and hopefully, we can start studying this right away.
Great.
Excellent. Have a great day. We'll be in touch soon. Thanks for staying up late. I know you're probably, is it the middle of the night?
It's nearly 12. It's 20 past 12 now.
All right. Well, I appreciate you staying up late for us over there on the other side.
No, I've been fascinated by I've been listening all evening, so it's great.
Well, we're on YouTube too, if you need to go to bed and catch us tomorrow.
Yeah, thanks.
Thank you so much. Have a great day.
Good night, everyone.